All right, good morning. My name is Nick Zhou. I work at the University of Tennessee, Knoxville. So today I will be talking about a fairly, I would say still at the preliminary stage study of using CO2-derived CNTs and nano-structured carbon in 3D printable concrete mixture. So this is a collaboration between University of Tennessee and Sky Nanotechnology. So Sky Nano actually is a startup spun off from Vanderbilt University. The founder, Dr. Anna Douglas, she did her PhD in chemical engineering and started a process very interesting. I'll talk a little bit about it in the presentation today. So I'll talk a little bit about the background in concrete decarbonization and the process of converting CO2 into nanostructured carbon and the dispersion of that into cementitious system and some preliminary tests on the 3D printing side that we have done in our lab, followed by some conclusions. So as we all know, cement manufacturing is a carbon-intensive process, so the CO2 emission primarily come from two sources. One is the heating, the combustion of fuels, release CO2, of course, and the decarbonization of calcite from limestone also produced a fair amount of CO2. So in that sense of trying to decarbonizing cement and concrete, we take two approaches. One is trying to beneficially utilize CO2 in some way of producing value-adding product, and at the same time, in the concrete manufacturing, we try to reduce the use of cement, Portland cement as much as possible, often in the form of increase the use of SCMs or complementary cementitious material. The thinking process for this project is that can we try to combine these two approach and maybe find a synergistic way of using both technique trying to decarbonizing cement and cement product. So one of the technology, again, this is a development from Sky Nano, is a electrochemical process. This is not invented, per se, recently. This has been discovered over 100 years that in a molten salt reactor, typically use lithium carbonate, and using an electrofield that the carbon is going to deposit on the cathode side, and the CO2 is used as a feedstock in the reaction, and the oxygen is released on the anode side. But until recently, that's the PhD study of Dr. Douglas and Sky Nano is the discovery process of by templating the surface structure of the cathode. You can essentially control how the carbon is deposited in its morphology. So going from carbon nanotube to very larger size carbon particles that I will show in a little bit later. So the thinking process is if we wanted to consume the CO2 that's released from the cement manufacturing process, this is an early stage sketch that can we take the exhaust gas from the cement kiln and use that in the reaction of producing a carbon nanoparticle. And once again, this process, by controlling how much electricity is being passed, the current that's passing through, and as well as the cathode structure, they can produce different forms of carbon, going from smaller diameter carbon nanotubes to what they call it carbon zoo. So it's larger carbon particles. They have explored applications in batteries, tires to replace carbon black in that sense. But for us, that goes in this process, we're thinking can we use part of that carbon that's been produced in synergy with SCM to produce a lower carbon footprint concrete product. So that's the goal. And In that process, of course, the challenge is dispersion. That's something that we looked at first in this research. Dispersion of CNT in cementitious system has been studied for quite a while. There are just different ways from mechanical sonication to chemical. You can do surface grafting or use dispersion to trying to disperse the particle. So one of the challenge, of course, is once following the dispersion process, often to use that in a cementitious composite system, we want to have a stable suspension before that gets mixed with cement. And having a longer storage shelf life is challenging because those nanoparticles, once it's dispersed, it tends to agglomerate. So one of the thinking is if we use SCM in conjunction with the dispersant, can we use the SCM somewhat as a carrier to deliver the nanoparticles in cementitious system? So we started that experimentation by simply mixing SCMs with the slurry. We tried fly ash, both fly ash and silica film together. So in that process, so we follow first in the sonication with dispersant, very typical way of dispersing CNTs. And then we added SCMs, again, in this case, both as fly ash and silica film to produce the slurry. Does it work? Of course not. That's just part of the life. After about a day, it's still separated. Now we see the deposition of the SCM particles on the very bottom, and then the carbon forms a layer, and everything is separated. So second, well, we took some slurry, put it under SCM, and can clearly see fly ash stay fly ash. There's nothing really attached to it, and all the nanotube is still agglomerate around it. So going from there, then we say, can we just change things a little bit? So we added latex particle, because before we had another project dispersing CNTs in latex, and was fairly successful and easy to do, and latex is added into concrete. We say, why not? And we basically use a polyamide latex polymer, and hoping some of those functional groups on latex polymers and to associate with the dispersant and attach that to the SCM surface. So we simply, again, mix those ingredients, and separation happened again. And in this time, and we just simply added another layer of latex to separate it from everything else. So we started wondering what we did wrong. And here is where we started figuring things out, is by adding a high shear emulsion process where, again, the emulsification use a high-speed mixer, and the vortex process through all the SCMs and latex particle. It's a physical process, but really, I think what happens there is that it forces the interaction between the surface of the carbon with the latex, and most importantly, you start to break up some of these SCM particles. I think Professor talked about before. It releases metal ions into the solution. That's really the cross-linking agent that's needed in the process. And finally, we started getting stable suspensions. Even after about 3 days setting there, it doesn't separate anymore. So we further take that under the SCM, trying to look at it, and the nanotube started to coat the SCM surfaces. So those are just more pictures of showing in that process how it started to wrapping around all the SCM particles. And then we started experimenting if we deliver that, just mixing with cement paste. And the hope is that because the suspension carry, the SCM is used as a carrier to deliver the nanostructured carbon in cementitious system, and in the hydration process, it will help with the dispersion. So With that made, we started to look at how it interacts with cement, because one of the important things is we use latex in the system, and we have to be careful because the latex, if we had too much of that in the cement paste, it will retard it. But if we don't have enough because it's quite essential for how we did the dispersion, then it affects the dispersion itself. So what the variable that we design is we fix the dosage of carbon nanotube, in this case 0.05% of cement mass, and changing, well, in this case we also fix the amount of fly ash and silica fume, 5% silica fume and 10% of fly ash, but we change the amount of latex polymer that's being used in the process. So this is the heat of hydration, as you can see, from 0 to 2% for fly ash. Essentially, the heat of hydration is not changed in that process, but we show slight acceleration. That's due to the carbon nanotube. But any excessive amount into 10% is start to have a retarding effect. So that's for fly ash, and that's where we kind of come to that 2% is the magic dosage for that particular amount of silica fume and CNT that we use in that system. And fly ash, it's similar story that we basically change how much latex polymer we're adding to the system. In this case, it peaked at 1%. So when it getting into 2% and above, it start to drop. So this is pretty obvious because silica fume has a much larger surface area, and therefore the amount of the surface that can be combined with latex polymer is much larger, and even with a lower dosage, and we see a higher tolerance of how much latex polymer we can add into the system. The difficult part for us, I think we had a little bit discussion in the committee meeting before, is how should we really quantify how well the particles are dispersed in hardened cement. What we try to do is we try to use FTIR to see how well the CNT is dispersed in the system. The approach that, well, the thinking process there is that because we know how CNTs is essentially going to affect the FTIR spectrum. There are many early research that have done in this area that we were trying to see because that with all the mixtures that we use here is the same amount of CNT that we mixed in. By having a more pronounced effect of the hydration acceleration and also the inhibit of carbonation, we're trying to see if with the process that we have help the dispersion, which the FTIR spectrum is showing that trend, and with the latex polymer emulsification process that essentially it pushed towards where we wanted to them more pronounced effect. And then we did try to find evidence to under the SCM to look at the dispersion. This is the case that we don't have any latex and emulsification process, that we still see agglomerates of CNTs and virus spots. Just showing a couple of examples here, and you can see in the background there's not much CNT present. And this is the case that it carries fly ash. The fly ash surface is very clean, and you have large clumps of CNT forms nearby, which indicate it does not disperse well in those cases. So this is the samples that we took with use silica fume as a carrier, and it does show under SCM that the nanotubes are dispersed quite a bit better in those cases. It does not, again, eliminate all the agglomerates, but it reduces in our observation. So And then we run some additional experiments and just trying to look at, because of that effect, can we synergistically bump up the dosage of SCM in conjunction with CNT, because with normal mixing, we know the dosage is typically capped around 0.5%, but in this case, can we go higher, 1%, 1.5? The result is promising. So basically, what we have in the observation is if we use SCM as carrier just to attach the CNT to its surface and use that to deliver into the cementitious system, we can get dosage quite high without completely changing the rheology. So again, this is some examples with high amount of CNTs and high dose of silica film. You can still see this silica film is acting as a carrier medium in this case to try to disperse that. So this is a preliminary the study that we did. We were trying to make functional cementitious system with higher dosage of CNT, use that for 3D printing. The little bit different what we did with this study from the previous. So previous, the CNT morphology is very much like CVD produced CNT, but in this case, since we're doing it for 3D printing, we communicated with Sky Nano, say we want your largest sample size, which I think is a mistake, but I'll show you in a second why. And so we basically made those mixtures, and we run all different kinds of study from the rheological properties, and as you can see, we added a dosage of CNT, the shear stress started to increase and decreased. And there's not a significant change, and a lot of results I'm showing here, we wonder why it doesn't behave like a CNT, and that's what we later find out. It's not CNT that we mixed in. So we did an extrudability test with the similar cock gun, but we actually have a lab scale 3D printer in our lab. The reason we had to stay with the approach is at the time we run this experiment, Sky Nano has about 200 grams of CNT that we can play with, 20 grams of CNT that we can play with, so we have to work with very limited material. This is the effects on the mechanical property. Young's modulus doesn't change. After we run the experiment, we're wondering why that happened, but mechanical strength does increase. So you have electric conductivity decrease, that's as expected. That's where we really break the sample, started to look at that under the SCM and find out the largest particle size that they grow out of from the chamber is really microfiber. It's not CNT anymore. It probably have close to about 100 nanometer in diameter. And again, this is very preliminary. The next batch, we're going to go back to the smaller diameter CNT and keep doing the experiment. I just wanted to cap on the conclusion. This, again, is a fairly early stage study that we're experimenting how CO2-derived CNT can be used in the cementitious system. And it's an interesting journey so far because they really have the ability to tune the morphology of the carbon, and that changes largely the interaction with cementitious system. With that, I want to thank the sponsors, Naval Research Office of Naval Research, Department of Energy, and our collaborators with Ash Grove and Oak Ridge National Lab.